Hello and welcome back to Artful Bytes and to another video in a series of videos where I'm programming an embedded system from scratch, or more specifically, this sumo robot. In the previous video where I introduced this project, if you haven't seen it, go check it out. I said that these videos are primarily going to be about programming, but before we get to the programming, I want to first talk a bit about the hardware. Because when we are programming an embedded system, what we're essentially doing is writing code to control hardware. So I think it's important that we at least have some understanding of it before we start programming it. And even for a relatively simple project like this, there's still a lot of decisions to make regarding the hardware. So I thought a good format for this video would be for me to start from the beginning and explain how I picked the parts for this project. This should give us a good structure to follow as we build up an overview understanding of the hardware, and should also give me an opportunity to give you some more background and context. And in the next video I'm going to do a walkthrough of the PCB I designed to connect the parts, and after that we get to the programming. So let's get into it. I want to first show you a block diagram I drew of my sumo robot. This block diagram shows the parts that I picked, the sensors, the motors and the batteries and so on, and what interfaces they use to connect to my microcontroller. I just wanted to give you this overview first before I start talking about each part. I will get back to this diagram at the end of the video. Before kicking off this project, it was just as with any project, only an idea. And then I had to figure out how this sumo robot was to come about. At this stage, a project can be pretty vague, but it's not like a sumo bot hasn't been built before, so I already knew before I even started kind of what I was going to build and what parts I was going to need. And as I explained in the first video, the rules for a sumo robot competition are simple. Two of these robots are put inside a circular platform called a Arduino, and the one that pushes out the other one first is the robot that wins. And from these simple rules, I already knew what my sumo bot had to do. It had to locate the enemy, it had to push the other enemy out of the ring by driving towards it, and it has to stay inside the Arduino. And further on, the competition has some rules which further help me define the requirements for my robot. First of all, there are several different weight classes, but I decided that I wanted to compete in the mini class, which meant that my sumo robot couldn't be larger than 10 by 10 centimeters and 500 grams. And with these limitations, I had already limited myself quite a lot in terms of what components I was going to be able to pick. And secondly, it has to be autonomous, which is an aspect that makes this project a bit more interesting in terms of programming. And you also have to be able to start the robot remotely, because at the beginning of a competition round, the judge will use a remote control to start the robots at the same time. And there are also some things the robot is not allowed to do. Most importantly, it's not allowed to intentionally harm the platform or the other sumo robot. I mean, this is not as fun as Robot Wars, perhaps, where the robots are allowed to destroy each other, unfortunately. Furthermore, it's not allowed to stick to the platform, so it's not allowed to have a suction mechanism or glue that gives it some unnatural amount of traction or friction. And two things worth noting is that the platform is 77 centimeters wide, and one round can't last for more than 3 minutes. These metrics were important to consider when I was picking my sensors and my battery. And with these requirements in place, I could start think about the parts I was going to pick. It was quite obvious that I was going to need some input sensors to locate the enemy and to detect the surrounding edge, and to drive towards the enemy and push it out, I was going to need some input motors. And since it had to be autonomous, I needed a controller to make sense of the input and to produce a desirable output to the motors. These three was going to be electrical, so I obviously needed a way to power them as well. So beginning with the motors, I had two main questions I had to answer. I had to decide which motor I was going to use and how many motors I was going to use. There are many motors to choose from, but by considering the requirements of a sumo robot, I could start narrowing down which type of motor that would be most suitable for a robot like this. First of all, a sumobot is a robot that drives around continuously. It's not like there is any mechanical movement that requires an exact positioning. So I could quickly rule out any type of servo or stepper motor, basically any positional motor. And I also knew that I was going to power it with a battery, which meant I was going to get DC and not AC, so I could discard all kinds of AC motors. And this meant I could narrow down my choice to some sort of DC motor. And when considering DC motors, there are mainly two types of DC motors. There are brushless DC motors and there are brushed DC motors. I'm not going to go into detail exactly on the difference between these two types of motors, but in summary, the brushless DC motor is the better motor because it's more efficient, has lower noise, and is more durable. But of course, that comes at the price of being more difficult to control. It requires more complex software, and it also requires additional electronics, and it's more expensive. For a sumobot, I wouldn't say that durability, efficiency, or noise are that important. So I would say it's overkill to put on brushless DC motors. And looking at other sumo robots of this size, I saw that almost all of them used brushed DC motors. So I also decided I was going to use brushed DC motors for my sumo robot. And then came the question of how many motors I was going to use. And considering the size of this robot, you're kind of limited in how many motors you will be able to fit mechanically. I would say that at most 6 motors, but that would require you to have quite small motors and small wheels. So maybe the reasonable choice is between 2 or 4 motors. My thinking kind of went that if I were going to use 4 motors, that would give me more pushing power because I would have more motors, which meant more power and more torque. But at the same time, having 2 motors would make the design more simple and it would make the steering more clean because having 4 static wheels won't turn as smoothly as having 2 wheels. But as you can see, I went with 4 motors, primarily because of the additional pushing power. Now in hindsight, I think I would have gone with 2 motors because it would have made the mechanical design simpler and more flexible, and it will also just have made the electronics design easier because in general the less parts you have, the less things you have to think about. And if I had gone with 2 motors and 2 wheels, I could perhaps have used larger motors and in turn gotten a similar pushing power as opposed to having 4 motors. Another thing that I didn't consider but that would have been worth considering and that I've seen some other robots use is to use tracks, just like tanks have. That should probably give some good traction and torque, but it wasn't something I considered for my robot. Knowing I was going to use 4 brushed DC motors, the next step was to find the exact motor I was going to buy. And brushed DC motors are spec'd with a lot of different parameters, but I mainly concerned myself with the input voltage, the voltage level it takes from the power supply, and the RPM, revolutions per minute, which tells how fast the motor spins. And to estimate the RPM I needed at this point, I came up with a ballpark value of the speed I wanted my sumobot to have. And I thought that maybe 2 meters per second would be reasonable because that would allow my sumobot to drive across the platform in half a second. Now in hindsight, that was a little wishful thinking because my robot is not able to drive that fast and still keep up with detecting the enemy and detecting the border. And regarding the wheel radius, I hadn't actually picked out the wheels at this point yet, but I kind of knew mechanically how big the wheels could be. So with the value for the speed and wheel radius, I could calculate the estimated RPM I was looking for. And the value I calculated was somewhere around 400. But when I went looking for a suitable DC motor, I saw that many of them are spec'd with a much higher RPM than I was looking for. And this is because by default, at least small DC motors are designed to have a very high RPM, high speed, and a low torque. And to fix this or to adjust the balance between RPM and torque, they must be equipped with gears or gearboxes, similar to how the engine in a car is complemented with gears. And while you can buy the motors and the gearboxes separately and then attach them together, it's easier to buy a brushed DC motor that comes with a gearbox attached to it. And when it comes to the voltage for a robot of this size, common values we'll see are 3, 6, 9 or 12 volt. And in terms of performance, it doesn't really matter which voltage you go for. What's more important is to consider what power supply you're going to use. So at this point, I also started thinking a little bit about what battery I was going to pick for my robot, because that would determine the voltage level I would input to my motors. And I found 2 single cell LiPo batteries with a good form factor for my mechanical design. So that would yield me a 7.4 voltage. Therefore, I thought a good input voltage for my motors would be 6 volt. I think my general advice when it comes to motors, given my limited experience with them, is that if you don't have much previous experience with motors, I think it's better to just buy a couple of different ones and try them out, prototype, and get a feel for what works, instead of trying to calculate the perfect specs. Because at least for small DC motors like these, if you buy them from cheap vendors like eBay or AliExpress, you can't really trust the specs anyway. If you want to trust the specs, you have to buy them from a trusted brand, which would be much more expensive. In the end, I picked 4 brush DC motors, spec'd at 400 RPM at an input voltage of 6. And similar to the motor I'm holding here, they came with a gearbox attached to them. I also bought 4 wheels with silicone tires attached to them. I picked them up at an online shop called Sumo, which sells sumobot parts. After having picked out the motors, I started looking at how I was going to control them. And as I mentioned earlier, controlling a brush DC motor is much easier than controlling a brushless DC motor, because brush DC motor basically takes voltage on the input and then produces a proportional speed. So the way we vary the speed of a brush DC motor is to vary the voltage we input to it. But it's not as simple as connecting the brush DC motor directly to the I/O pin on a controller chip, or for example the GPIO pin on a microcontroller, because a GPIO pin can't source the amount of current required by a motor. So if you even try to, you might even damage the microcontroller chip. What I needed was some sort of electronics in between my controller chip and motors to be able to control the motor. More specifically, something called a motor driver. And a motor driver is a chip that contains transistors that act as switches. And we connect these switches to an I/O pin on our controller chip. And by toggling the I/O pin, we produce a pulse width modulated signal that allows us to switch these transistors on and off to vary the voltage output, and in turn control the speed of the motor. So the motor driver connects to the battery, and the larger current from the battery is controlled by the smaller current from the controller chip. I will talk about this more in a future video when we program the driver for the motor driver. There are 2 common types of transistors used in motor drivers: BJTs and MOSFETs. In short, the MOSFETs are better because they're more efficient and produce less heat. So it's preferable to pick a motor driver that has MOSFETs instead of BJTs, because then it's less likely you will have issues with your board overheating. In the end, the motor drivers I picked out for my sumo robot was the TB6612FNG. These motor drivers are MOSFET based, and they can produce up to 1 amp of constant current and around 3 amp for short periods. And they are able to operate between 2.5 and 13.5 volts, and also include some protection circuitry. They're able to control 2 motors, so since I had 4 motors, I needed 2 of them. But also note that on my robot, I have 4 static wheels, and the motors on either side should always drive in the same direction. So when I hook this up, I actually use the same input signal from my controller chip to produce the PWM signal for both these motors. So I only actually need 2 PWM signals, but I will talk a bit more about that later. Having the motors and motor drivers picked out, the next thing I started looking at was the sensors. And the sumobot needs sensors for 2 purposes. First and foremost, it needs sensors to detect the enemy, and secondly, it needs sensors to detect the surrounding edge border of the platform. And let's start with the first one, the sensors I needed to detect the enemy. Okay, so starting with the enemy detection, when I had a look at what other sumobots were using, I quickly realized that none of them use a camera for this purpose. And I guess that makes sense, because a camera would require a more beefier controller and more complex software to parse the video stream, and it would probably not be as fast or reliable as I want. And it would kind of be overkill, because all that the robot really needs is a way to detect the distance to the enemy. So it should be enough with a simpler range sensor. Having a look at the available range sensors, there were a couple of different options I could choose from. There are ultrasonic sensors, and these measure the distance by utilizing sound waves. And there are IR sensor, which sends infrared light and measures the amount of light reflected back. And then there are different types of laser-based sensors that also utilizes light, but mainly measures the time it takes for the light to travel back and forth from the obstacle. Looking at available ultrasonic sensors, I quickly ruled them out for being too bulky and slow for a small sumo robot. And looking at the difference between these, I would say that the IR sensors that I was looking at seemed to have a simpler interface, but they were also a bit limited in terms of the range interval. They could either measure at a smaller interval, like between 0 and 10 centimeters, or a longer range, 10 to 80 centimeters. And I wanted a sensor that could measure from 0 to around 80 centimeters, because that would allow my sumobot to detect the other sumobot regardless of where on the platform the other sumobot was. It could be right in front of my robot or on the other side of the platform, and my robot would still be able to detect it. And to give you an example, this was one of the IR sensors that I tried out for my sumo robot. And even if this was smaller than the ultrasonic sensors that I found, it was still a bit large for my sumo robot, and it couldn't measure very close distances. So if I were to use this, I wouldn't detect the enemy if the enemy was right in front of the sumo robot. Instead, I found smaller laser-based sensors that seem to be the perfect fit. This is a tiny time-of-flight laser-based sensor from ST. It's a small and powerful little sensor that comes at a surprisingly low price, and it measures accurately between 0 and 2 meters at a frequency at around 50 times per second. It's also quite cheap. The downside, of course, which I realized later, is that it takes quite some effort to get this working, because it interfaces with I2C and has a microcontroller on it that requires quite a lot of configuration and setup code, and especially when using more than one of these sensors. But other than that, it's quite hard to find something better at this small size. After selecting the range sensor I was going to use, I had to, similar to the motors, decide on how many of them I needed. First, I could conclude that I was at least going to need one of them, but having only one range sensor in the front would mean that it would be hard to distinguish between different cases. The enemy could be oriented in different ways, and it could lead to my robot attacking the other robot in a non-optimal way. So I realized it would probably be better to use more than one range sensor in the front, because then I would know if the enemy was a bit to the left or a bit to the right or right in front of my robot. And if it wasn't right in front of the enemy, I could use these measurements to make sure that my robot aligns with the enemy. Next, I considered putting range sensors on the two sides, because that would kind of allow a strategy where my robot could detect the enemy on the side and then could do a quick arc turn and attack the enemy from the side. I didn't really consider putting a range sensor on the back. Perhaps that could be useful if the enemy is pushing my robot from the back. So with this kind of thinking, I ended up going with 3 range sensors in the front and 1 on either side. Now in hindsight, I would have just gone with the range sensors in the front, because after some time I realized that the range sensors on the side didn't work so well, because it actually mattered the way you oriented these sensors. So I got a lot of false detection the way I placed the side sensors. And I also found that using the front sensors just worked well enough. And it was unnecessarily complicated to have 5 of these sensors, because as I said before, they're a bit finicky to interface with. And having 5 of these connectors were a bit troublesome. And it would have just been easier overall mechanically to have 3 of these sensors instead of having 5 of them. So I'm kind of getting back to my advice that I gave regarding the motors. The less parts you have, the less problems you will have. When it came to the line sensor, that was a fair bit easier, because it essentially came down to just one choice. An IR sensor that could distinguish the white border from the rest of the black platform. So the one I picked is called QRE113 and interfaces with just one ADC pin. I put 2 at the back and 2 in the front. It's perhaps not necessary to have 2 in the back, but it allows my robot to get out of a few more situations. And there is not much more to say about the line sensors really. On the topic of sensors, my robot also required eye receiver to pick up the start signal that is sent at the beginning of a competition round. So I picked up this 3-legged component, which is an eye receiver that can pick up the start signal that is specified at 38 kHz. Besides meeting the requirement of being able to pick up the start signal, a very useful thing with having an eye receiver like this is that it also allows me to control my robot remotely, which is very useful during development. And with the output and the input out of the way,
now is a good time to talk about the power supply I used for this robot. And there are many types of batteries you can choose from. But what you will commonly see on smaller robotics projects these days, or even hardware devices in general, is that they use some sort of LiPo battery. And this is for good reason, because LiPo batteries packs a lot of energy in a very small package. And it comes in many different shapes and forms, so it's easy to fit a LiPo battery into your mechanical design. To last through the competition, I knew I didn't need a very large battery, because each competition round only lasts for at most 3 minutes, and probably most of the time shorter than that. But it's nice to have a larger battery during development, because you don't want to be switching out the battery all the time. And I was also a little concerned with having a small capacity, because while LiPo battery discharges, it loses some of its voltage, and unless I compensate for that, that would mean that my robot loses some of its pushing power as the battery discharges. So capacity-wise, I was just trying to fit as large of a battery as I possibly could, but having 4 motors meant that I didn't have that much space over for batteries. What I found during my search were 2 small single-cell LiPo batteries that had a capacity of 750 milliampere hours. Since they were single cell, they had an output voltage of 3.5 voltage, and having these in series meant I had 7.4 voltage in total. And I had a discharge rate of 30C, which is well beyond what this robot would need to source at worst case. This battery is actually meant for a drone, but it works pretty well for my robot as well. I had plans on making the batteries easy to swap out, but I couldn't come up with a good mechanical design to do that without making my robot very bulky. I also thought about having separate batteries for the electronics and the motors, because I was afraid that the noise from the motors would interfere with the rest of electronics, but it's not something that I've had any issues with. Okay, so now I had picked out the surrounding parts. I picked out the input, that is the range sensors and the line detectors, and I had picked out the output, that is the motors. And now it was time to pick out the central piece of this robot, the piece that would take the input from the sensors, do some processing, and then produce a desirable output to the motors to make this robot behave as it should. Before I go on to talk about how I picked my microcontroller, I want to first explain why I didn't go for an Arduino. I'm not trying to pretend that this robot is anything but a toy project and a relatively simple robot. And for a project like this, an Arduino would be the obvious choice. It would provide the required functionality and make the programming easy. And if I wanted to throw this together as quickly as possible, I would probably have picked an Arduino or similar and call it a day. But I wanted to develop my sumo robot more like a real product. I wanted to pick my computer chip and design a PCB around it, and then write the drivers for it. I wanted it to be more than just plug and play, so that I would actually get something out of the project. And I can tell you that if you want to get more serious about embedded development and move on to more advanced projects and perhaps work on real products and do this as a profession, then you must leave the comforting world of Arduinos and get your hands dirty with other chips. And I think a good way to get started can be to pick a simple project like a sumo robot that would typically use an Arduino, and then replace the Arduino with some other chip that forces you to do more of the hardware and software yourself. And it may seem stupid to overcomplicate a simple project, but once you get comfortable at that level, then you can advance to more complicated projects where an Arduino is not even a viable option. Note, I'm not saying that an Arduino is a bad thing, or that embedded systems development always mean that you pick a microcontroller and then write all the code from scratch just for the sake of it. I'm all for taking advantage of the resources and tools that helps you develop your project faster. But there's so much more to real product development than just prototyping, and if you want to work on this side of the product development, you will need to know proper embedded systems development and everything that comes with it. You will need to know how to pick the right parts, the right microcontroller, how to design a PCB around it, how to write a driver, and so on. And it's in this area I want my YouTube channel to be focusing on. And since I wasn't going to limit myself to an Arduino, the next question became what I was going to use instead. And there are many chips to choose from. Everything from tiniest 8-bit microcontroller with a few hundred bytes of flash to high-end ASICs running full-blown operating systems. And if you develop a real product, choosing the right chip is an important decision, and a lot of research can go into making a good choice, especially for a high-volume product where every cent counts. But for a one-off hobby project like a sumo robot, I didn't need to be near as rigorous in my decision making. What it roughly comes down to is listing out the things that the chip is going to be connected with, which is basically what I've done in this video. We've gone over the parts I'm going to use, and based on the surrounding components, I can start listing out the interfaces my controller chip requires to talking with them. And then from this, I can start sketching out some of the requirements that my controller chip needs to have. For example, the peripheral, the code size, clock speed, power consumption, and so on. For this simple robot, there are many chips that would get the job done. It might even be harder to pick a chip that wouldn't work than one that does work. And while it can be tempting to pick a very powerful chip for a simple project, that will just make the hardware design and software design more complicated. Now, there was no good reason to put on a high-end application processor running an operating system when I could get away with a simpler microcontroller. So I limited my search to the microcontroller segment. And according to the flow that I just described, I started listing out the interfaces I required based on the components that I had chosen. 2 PWM signals to control the motors. I was going to have 5 sensors that was going to talk over I2C, so I would need an I2C peripheral. And for the line detectors, I was going to need 4 ADC channels. And then I was probably going to need some timer and GPIO for the I receiver, as well as an additional of 10 or more GPIO pins. And then there were some other factors to consider. And when it came to clock speed, I knew I didn't need anything super fast because there is no heavy computation required and the processing speed is limited by how often I can get input from the sensors, which for the sensors I picked were somewhere around 30 times per second. Regarding code size, that can be a bit difficult to estimate if you don't have previous experience with a similar project. But a good idea at this point can be to look at what similar projects use. For example, an Arduino seemed to do fine on a lot of sumobot. So having a look at the microcontroller on an Arduino seemed like a good idea for getting a rough ballpark value. So the Atmega 328 on the Arduino is an 8-bit microcontroller. It has 20 MHz clock speed, 32 kilobytes of flash. Regarding power consumption, I didn't really concern myself with that because I was not going to have any low power mode, and I knew that the power drain from my microcontroller would be negligible in comparison to my motors and other components. And regarding price and the available stock, this is also something that I kind of discarded because this was a one-off hobby project, so it didn't really matter if the microcontroller would cost me $1 or $10 or 10 cents. Of course, price and available stock is a much more important question when it comes to a high volume product. And then to a factor that must not be underestimated, which is ease of development, including the available tools surrounding documentation, tutorials, forums, and so on. Things that makes the microcontroller pleasant to work with. Because picking a microcontroller that is pleasant to work with is going to save you so much time and frustration. After I had a decent idea what I was looking for, I started searching on the internet for a microcontroller that would fit my requirements. So I had a look at DigiKey, Mouser, and other components vendor and used their search to list my requirements and to see the available microcontrollers. And I also did some general searching on the internet for recommended microcontrollers. Finally, for this bot, I picked the MSP430, which is a 16-bit microcontroller with 16 kilobytes of ROM and 16 MHz of clock speed. I mostly picked it because I had used it before and I knew it had good documentation, books, tutorials, forum, and overall provided tools for a pleasant development experience. It's actually commonly used in university for getting started with embedded systems and can be considered a beginner-friendly microcontroller. And I think this will be a good microcontroller to use throughout this series. Regarding the technical specs, it's perhaps not the optimal choice for a sumobot. The flash or the ROM is on the small side. It has few pins and few dedicated PWMs. It's really meant for smaller, low-power devices. In hindsight, I think I would have picked a beefier microcontroller. Just having some extra flash and a few extra pins would have made things easier. But it worked out anyway in the end. If you're someone who's just getting started with embedded development and is about to pick your first microcontroller, I would say go for something simple, maybe an 8-bit microcontroller that is well known. And don't be afraid of making the wrong choice. If you prototype, you will find out soon enough if you made the wrong choice. And all microcontrollers fundamentally works the same way, and what you learn on one microcontroller applies to other microcontrollers. And as a hobbyist, you have the luxury to make mistakes. It's a whole nother question if you're picking a chip that will be placed in millions of devices. But that's not what we are doing here, not yet at least. Okay, so now I've gone through everything I wanted to cover in this video. It got a bit longer than I expected, but I think it was a good idea to talk this through, because as I mentioned in the beginning of the video, embedded systems development is so much about hardware, and we must really understand the hardware when we are programming it. And this video also gave me a chance to give you some more context and background around the project, which I hope will be helpful for following along in the coming videos. Okay, so just a quick recap. I started by talking about the motors and the motor drivers I picked out. And then I talked about the range sensors and the line detectors, as well as the eye receiver that is needed to remotely start the robot. I also talked about the power supply, and finally we got to the most important piece, the microcontroller. I didn't talk about this part here, but I will do that in a future video. I will get back to this diagram throughout this video series, just to keep ourselves oriented as we go about writing the drivers for the individual parts here. Okay, this is all for now, and in the next video I will do a walkthrough of the PCB design that I made to connect all of this, and then we will get to the programming. So see you in the next video. Artful Bytes.